Take a look at exponential relations and try to figure out whether or not a table of values represents an exponential relation. And so what I have here on the left-hand side is a table of values, very similar to what we looked at when we did quadratics. And so what we want to do is we want to figure out the differences that we see happening in this particular table of values. So just like we did with first differences, or with quadratics, we want to find the first differences, the second differences, and see if there's any connection there. Okay, so if I quickly find my first differences, I've got 8 minus 4. That first difference is going to be 4. Then I've got 4 minus 2. That's going to give me 2. 2 minus 1 is going to give me 1. 1 minus 0.5 is going to equal 0.5. And 0.5 minus 0.25 is going to equal 0.25. Okay, so obviously my first differences are not the same. Okay, so they are all different. So my first differences are not the same. So the next thing that we want to do is we want to say, okay, well, look, if the first differences aren't the same, then let's see whether or not the second differences are the same. So we know it's not linear because first differences aren't the same. Let's see if it ends up being quadratic. So let's find the second differences. So we're going to do 4 minus 2. That's going to equal 2. Then we're going to do 2 minus 1, and that's going to equal 1. We're going to do 1 minus 0.5, and that equals 0.5. And finally, we're going to do 0.5 minus 0.25, and that equals 0.25. So my second differences are also not the same. Okay, so it can't be linear, it can't be quadratic, so therefore, could it be exponential? Well, how can we tell? Well, one thing that we can see very clearly, hopefully, is that there's a connection between the numbers in all the second differences and the numbers in all the first differences and the numbers that are actually in the table of values. Okay, what's the connection between 8 and 4? Well, 8 divided by 4, 8 divided by 4 is equal to 2. 4 divided by 2 is equal to 2. 2 divided by 1 is equal to 2. 1 divided by 0.5 is equal to 2, and so forth. If I look at my first differences, I've got 4 and 2 again. Well, 4 divided by 2 is equal to 2. And 2 divided by 1 is equal to 2. And 1 divided by 0.5 is equal to 2, and so forth. And even if I look in my second differences, I see the same connection. I see that 2 divided by 1 is equal to 2. And 1 divided by 0.5 is equal to 2, and 0.5 divided by 0.25 is equal to 2, and so forth. So I actually have what we call a constant ratio. Okay, so when I divide, no matter whether it's in my original table of values, in my first differences, or in my second differences, I actually have a constant ratio between all of the y values, and that ratio is 2. So they can be either all multiplied by 2 or divided by 2. Okay, so if I wanted to go from 2 to 4, I multiply by 2. From 4 to 8, I multiply by 2. And so the next number down, if I kept going in this table of values, would be 16. And I know that because I can multiply 8 by 2 to get me 16. So this is an exponential relationship. Again, we talked about this a little bit back when we did our quadratics review in quadratics 1. But linear relationships, their first differences are always the same. Okay, and their highest exponent is 1. So this up here is a linear relationship because its highest exponent is 1. Quadratic relationships, their second differences are always the same, and their highest exponent is a 2. Well, right here, their highest exponent in this particular equation is a 2. And with an exponential relationship, the ratio between the values are always the same, i.e. they multiply or divide by the same number. In the example up above in that table of values that we did, it was 2. And it's important to note that the exponent is always a variable. So based on the fact that the exponent is always a variable, this particular equation here represents our exponential relationship because the exponent is a variable right here. Okay, the exponent is an x. Carrying on with the same idea, we want to look at features of exponential relationships. Okay, and so some of the features that go along with having an exponential relationship include the following. So differences between the values, between the y values. Okay, y values is a very important piece of that. Their constant ratio. Okay, so they're either multiplied or divided by the same number. Okay, and you can see that pattern in the original table of values, in the first differences, or in the second differences. The highest exponent in an exponential relationship is always a variable. Okay, so it's actually not a number, but it's a variable. Okay, so for example, could be y to the exponent, or is equal to 2 to the exponent x. Okay, and so again, x is a variable, and so that indicates that that particular equation is in fact an exponential equation. We also looked at different types of graphs. So what does a graph of an exponential relationship look like? And so a growth graph, or an exponential growth graph, is going to move up, okay, on an exponential rate. So it's going to start horizontal on the left-hand side and then radically move toward a vertical position as you move from left to right. Our decay graph is going to look the opposite. It's going to start from a vertical position and then move towards a horizontal position. Okay, and so that's going to indicate an exponential decay graph. So we could even put in, for example, an axis, just so we have an awareness of what that's going to be. Okay, and what's really important about exponential relationships is that the curve will never actually touch the x-axis. It continues to shrink and shrink and shrink, but theoretically never actually achieves 0. Okay. When looking at the formula for all exponential equations, the formula for all exponential equations is right here. Y is equal to a times b to the exponent x, and every single version of the form of the exponential equation is actually a variant of this particular base formula. Okay, so what does this formula tell us? Well, it's really useful actually because it tells us that the y-intercept, or the initial value, is always the a value. Okay, so the a value is the y-intercept, or it's the starting value. Okay, also sometimes called the initial value of what you're starting with. So in this particular example, where we have y is equal to 2 times 0.5 to the exponent x, the a value is equal to 2. Okay, that means the starting population of whatever it is we're graphing happens to be 2. If the b value is bigger than 1, okay, and in this instance, the b value is not in our example here, but if the b value is bigger than 1, what that means is that it's a growth curve, okay? And so we would end up having our axis And if the b value is bigger than 1, then it's actually growing. Okay, so it's growth. Similarly, if the b value is between 0 and 1, so it doesn't actually hit 1, the b value is not equal to 1, but if the b value is between 0 and less than 1, then that indicates that it's actually um, a decay graph. Okay, it's shrinking. So the value is actually getting smaller and smaller. And I'm realizing that that decay is not legible. So let's try and read that or write that again. So decay. Okay, so that's actually a decay graph. That means it's shrinking. It's decreasing in value. Okay. So I mentioned to you that every formula is a variation of y is equal to a times b to the exponent x. So when we do our formula for simple increase, it's actually going to be y is equal to a times 1 plus r. R is going to be the rate of increase expressed as a decimal to the exponent x. Okay? So r is rate of increase, or whatever your rate happens to be. Okay, so r is rate as a decimal. Okay. Our formula for simple decrease is very similar. Y is equal to a times 1 minus r to the exponent x. Okay, I'll just make that a proper 1. And again, the r value needs to be expressed as a decimal. And the last thing that we'll cover off here is formula for doubling time and for half-life. Again, doubling time is just a special variant of an increase rate, but because it doubles, it goes to 200% of what it was originally. So the formula for doubling time is going to be, let's see, your starting population or your final population is equal to your starting population or your PO or original population times 2 to the exponent t divided by d. Okay, where t is the actual time, so the actual amount of time that has gone by, and d is the doubling time, and usually the doubling time will be given to you in the question. Okay. The PO is the original uh, or starting amount of value, so it is the A value. The half-life formula is very similar to the doubling time formula, but in this case, instead of the population doubling, it's being cut in half. So in this instance, our half-life is actually, we call it M, is equal to MO, or mass of the original, times 0.5 to the exponent t divided by h. Okay, so t is the same. T is actual time. Okay, and h is half-life. And again, the half-life will be given to you um, in the question. Okay, so that just quickly covers off some of the basic characteristics of exponential equations that we are going to be using as we go along.